Good.
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 Got my COVID vaccine, so I'm feeling real good.
How long ago since you've taken it?
Got it like yesterday night.
Has it affected you?
Yesterday no, but now I'm feeling a little tired, a little warm, and a headache.
Oh boy.
Fun stuff. Regular flu.
Hopefully it doesn't get any worse than that. I guess I'm old because I feel like I'm still recovering from the time change. Like I didn't catch up on sleep.
I was getting ready for that all weekend. I think I started like Friday, sleeping like one hour early and waking up 1 hour early.
Yeah, I didn't prepare for it. Okay, so I think we can go ahead and get going here. Let me make sure that Microsoft Whiteboard was down earlier, so it comes back up. Okay, so it's up. So let's see where we're at. We're at ME272. Today is the 16th. So next week is spring break, right?
Yep.
We have the week off. Awesome. Okay, so we need to get a few more points. So I went ahead and loaded next assignment onto Canvas, and what that is we're gonna call this a midterm, but it's a low stress midterm. It's kind of like a book report. Are you able to see this through your Canvas?
Yes.
Okay.
I still see the whiteboard on the. Are you showing something else besides the whiteboard?
Oh, I was looking at my Canvas, so I guess it didn't keep up. Okay. So if you're able to see the thing pop up as midterm for a Canvas, then you're good to go.
Yeah, I see it.
So what we need, what it essentially is, and we're going to go over a little overview here, but it's essentially, I want you to do a kind of graduate level literature review. So you're going to go out, you can use Google Scholar or library resources or whatever your normal resources are that that you do research in. For those of you that haven't done research, this is a perfect opportunity to do that. But I essentially want you to find three sources, three published sources, and I want you to put together a literature review, a graduate professional level of this Navier-Cauchy relationship and how they came about elasticity. So we're gonna treat this as kind of like a midterm. It's 100 points. So essentially, if you put in a reasonable amount of effort, you find the three sources and you put together a somewhat coherent overview of it, ending in the equations, which I'm going to give you the equations right now, so you know what the target is that you're looking for. Then you'll be good to go. I don't want to impose this on anybody over spring break because that's just mean and rotten and unnecessary. So what do you think that you need for a timeline to do this? I can set it for the end of the break, and that's how I have it set up right now. So you have all of this week, the weekend, And then if you wanted to do it next week, so I think I had it set for the 30th. That's a full 2 weeks at midnight, or what are your thoughts?
How thorough are you thinking? Like really getting into the weeds of it, of all the everything that led up to it?
No, maybe I don't know, 2-3 pages. Nothing major.
That
That's
sounds like
pretty fair.
Anyone have commitments that would keep you from meeting the 30th? So that's 2 weeks from today at midnight.
Just thinking about going to Mexico for spring break, but I guess I'll pull the reins on that one.
Well, you could always do it this week.
Yeah, true.
Okay, so it's currently released in Canvas, and it's set for the 30th at 11:59 p.m. But essentially, we owe a lot to these folks, and I actually learned a lot when I read this. And I ended up doing my own literature review on this because I guess I nerded out on it and was interested on it. But I was forced to do an assignment like this at one point, and I don't remember when it was in school, but it was on the whole Leibniz calculus thing. And I learned a lot from it, and I thought it was really interesting to kind of pull real world type stuff into mathematics. So it's essentially the two French guys so we're going to do a literature review, and I would say 3 sources, and you'll probably all have overlapping sources or 3 references. I would kind of hit the history on each person, because they're both, what's interesting about them is they're engineers. They're not mathematicians. And that's what's cool about this. I think that's what's cool about it. And then essentially how the equations came about. And if you can, reach deep, what they mean. And I'll be curious if any of you find this. Excuse me. These equations are going to be in a little bit different form than what I've shown you in the class, but they're the same. So they essentially are going to be, remember how we've talked about this boundary value problem, and there's 3 pillars of equations: equilibrium, displacement, and compatibility. These equations end up being used with different variables, but in the same form. For fluid flow, for vortices, for all kinds of things that describe nature, not just elasticity. So I'm curious if any of you pick up on the trends for these and what they are. So let's go ahead and we'll review what the equations are in the form that you will see them when you do your literature review. So the first one's equations of equilibrium. And like I said, this is a different form than what you've seen. So I'm going to call this pillar 1. So that's consistent. But what you're going to see is written out a little bit different. So it's the partial of sigma xx with regards to x plus the partial of sigma yx respect to y plus the partial sigma zx respect to z plus bx is equal to 0. And as a reminder, before I write the rest of them out, what you have seen so far is Tij comma j plus rho bi equals 0, right? That's what we called it before. Isn't this the same equation? Because Tij comma j is a bunch of partials. So xx, yx, zx, that's essentially just 1, 1. Xx is repeated indices, and so it's just using those separate subscripts instead of 1s and 3s. But this equation right here on the left, does this look familiar with exception of the bx term, the body force term? If you were to cover the bx like with your hand or something, doesn't it look like an ellipse?
Yes, it does. Brings me back to DE.
Everything ends up simplifying to an ellipse. That's crazy. Okay, so that's equation 1. Then we have the partial of x sigma xy regards to x. See if you guys notice something else. So if you look at these 3 equations holistically, do you see anything interesting?
They have like the same notation for like a matrix.
Exactly. That's the key. That's 1. This is a giant matrix, right? But do you know, I'm going to put a dotted line around this because this isn't this is more of an aside. It's not related to the Novi-Cauchy. So this is a matrix. See the XX, YY, ZZ on the diagonal, YX, ZX, XY, YY, ZY, da, da, da. Do you know what that equation, what that matrix is called when you have the partials like that? It's a Jacobian. And it's essentially, the partial derivative for all of these. And if, like I said, if these weren't stresses, if these were something else, it's still the form of an ellipse. Okay. So that's our equations of equilibrium. Then we have our second pillar, which is our strain displacement. And this one is epsilon x is equal to the partial of your displacement with regards to x. Epsilon y is the partial of displacement with respect to y. And epsilon z equal to the partial of, oh, I take it back. This one's not u, it's a v. It's a sub. I'm using the same notation that you're going to find in your references. This is like a, not a, yeah, it's a v. It's not a Greek term. At least doesn't look like it. This one's w. These have commas after them. So these are the principles, if you will, EXX, EYY, EZZ. And then our epsilon YZ. So these would be our shear strains, right? 1/2 the partial of W with regards to Y plus the partial of V with respect to Z. And this is equal to epsilon ZY, because we're talking about elasticity and we're still assuming that we have a linear isotropic material. That means our diagonals are, we have symmetry. Epsilon ZX is equal to 1/2 partial of U respect to Z plus the partial of W respect to X. And that's equal to XZ and epsilon XY 1/2, again, the partials. So again, what when we're talking about partial derivatives of displacements, so this EXX, it's equal to the partial of the displacement U with in regards to X. What is that partial looking at? This is what is this term telling? What is it? Isn't it strain rate? Because we're taking partial derivatives. So we're looking at the rate of change. And then the third one, this one's going to look really odd, but it is equivalent. And this is the compatibility. Called compatibility relations. Or we call them Hooke's law, or it could be constitutive equations. Essentially, it's relating stress to strain. So these are a little laborious to write out. So we have the second partial of epsilon XX regards to Y plus second partial of epsilon YY. So we're taking the second partial derivative of our principles. And here comes our shears, partial X, partial Y, comma, partial squared, epsilon XX, regards to Y, Z, minus epsilon YZ, X, epsilon zx. Okay, so there's 2 more rows of this. And one of the things that I ask you to do when you are writing this is don't take a screen capture and dump this into your report, and don't handwrite it and take a picture and dump it into your report. Actually use like equation editor and make it look professional. I know it'll take a couple minutes, but you'll feel like you accomplished something. Y, Z, comma. While I'm writing this boring stuff out, do you guys remember, guys and gals, do you remember when you started studying algebra? Sorry, I'm a proud father. My 3rd grader is doing algebra now, and I was blown away. I didn't think I started that young. Did you guys?
You mean like it's officially part of his school program, or you just doing?
Yeah, yeah.
No, not that. Not officially. That no.
Yeah, I don't think so either.
I don't remember when I did. It was probably high school for me.
Yeah, we definitely were doing like a worksheet of like adding and subtracting in like 3rd grade
Yeah.
for me.
I used to tutor a girl in 5th grade,
Uh-huh.
and they were doing Common Core stuff. So they were like sort of starting to learn about percentages, but they tried to make them do it in a really weird way.
Yeah.
So like, you know, like A equals PB, which is like super easy to use for percents.
Mhm.
They were trying to get them to do it mentally. So like think of like what would 50% of like a dollar be type thing. But I haven't really seen since then like just straight up like algebra. I see like bits and pieces of them trying to like relate the different parts of algebra together and then going about it
Yeah.
that way.
Yeah, that's what they're doing. They're not trying to solve for a variable yet, but it's the equation's written, right? And they're mentally solving for it. They just don't realize what they're doing. So of course I had to show them the next step, and probably made his teacher angry.
How do you feel about Common Core?
I don't know. I think as
Yeah,
long
I
as
think
I think as long as they get it, it's fine. But how they get there, I don't necessarily think it's too important.
I just feel like what I've seen of it at least doesn't seem intuitive anymore. It just seems like a lot of backwards like workaround thinking. I don't know.
I've seen the opposite. To me, I've appreciated what I've seen, but it could be different from school to school, because
Right.
it seems like they're trying to teach you the why instead of just memorizing things. They're trying to get you to conceptualize
Yeah.
how the mathematics is working. And
Well, what it
they're doing
means,
kind of
right?
what I did when I was younger. I kind of came up with ways to think about it, and that's kind of what they're trying to tell you.
Yeah, yeah, and that's kind of my perception as well. Is because like some of the stuff where you round up to the next whole 10 or whatever, and then subtract it. I've been doing that forever. That was just the way that I kind of did it. But yeah, it's exactly that, Jacob. It almost seems like they're kind of forcing people to think that way in such a way. But
I think people get mad at it because it seems to take longer to do something simple, but they're building the concepts of how to do bigger things in your head.
it's the bigger and the why and the how. Yeah. So.
I think like me personally, when I was growing up and doing math, I appreciated more being just told like this is how you do it. And then as I got older, appreciating why. Because I remember being young and not like being able to understand and conceptualize very well. Like I didn't get those skills until I was much older. So I could see
Yeah.
like me going through it as a 3rd, 4th grader being very frustrated with mathematics and not wanting to do it anymore, as opposed to just being like, hey, this is how you do it. And then like appreciating why as I got older and like was more mentally capable of understanding it. But I mean, I guess there's no one way that's going to work for everyone. So
Yeah.
I just think Common Core is complicated.
It was the first time I saw it, and I'm like, what am I trying to teach him? Okay, this is a Z. You don't have to copy this down. You're going to find it. I just wanted you to see what this looks like. So you weren't shocked with it, but they're essentially the same equations. And that's part of what I want you to do with this is kind of when you stumble upon these, you should find some narrative about, you know, what they are and how they came about, and just kind of maybe compare and contrast to, you know, what I've shown you with how it's used today, and see if you can make the connections of, yeah, this really is the same relationships. It's maybe just written a different way, or I think it's pretty cool that they did this. I think it was, if I remember right, this all came about because of a vibrational equations in like 1921-ish or something, I think is when they came about. So definitely before computers were crunching through finite element analysis and doing stuff, which is pretty crazy. Okay.
Professor,
Yeah.
for the terms that have two partials in the denominator, does it matter the order that the partials are in? So like you could flip like the partial x partial y, it could be partial y partial x, and it would be the same. Okay.
Okay. So that's that. We'll call this little literature review our midterm. 100 points. It'll be due 2 weeks from tonight, 30th, 11:59 p.m. Unless I hear any objections. And what we'll do for tonight and then on Thursday is we'll talk about, I'll just kind of give you a really high level overview of what the St. Venan's principle is, or St. Venan's problem is. Talk about plane stress, plane strain a little bit. And that'll take us to the end of this week for spring break. And then when we come back, elasticity is behind us and it's finite element. Okay. Sound good?
Yeah.
Yeah. Okay. So I'll kind of separate this. And there's a lot to this St. Venan's. I probably have 20 pages of notes on this, which we are not going to do. We're going to do just a couple to give you the concept of it. It's a very simple concept. And we don't have to get into the the nuts and bolts of the theory, but it's called St. Venan's problem or principle. And before I even describe what it is, or before I get into it, let's say that we had a simply supported beam, and we were to infinitely fix it right here, and we were to put a load on it here. And we're displacing this, right? It's gonna, I don't know if I can do this. Right, we're going to get some deformation out of it. And you guys know from undergrad and ME180 that how do you find the stress of this? Put a center line. That you're doing it by hand.
Isn't the equation just like sigma equals my over I?
Yeah. So stress is equal to my or mc over I, depending on how you learned it, right? And what is m again?
Moment.
So m is our moment. So that's our distance from our coordinate system here, right? So using our, say this is x1, x2, x3. So moment is our distance, right? And our y is our distance to our neutral axis, right? And then we have our inertial term. Can we find the stresses out at this interface right here? Right there on the x3 axis?
No.
Do we know what they are? Nobody said that, right? We can actually, yeah, if we were an ME180, we could calculate what the stress is there and we're like, sweet, I got an A, right? But the reality is, think of this as a little bit different now. Let's think of this as some sort of, let's think of it as a 3D printed part and you had layers and you had a bunch of these tiny, 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 tiny little layers. And you put a load on it and it was fixed here. And let's say you displace it and instead of displacing, it actually broke. And let's say what you ended up getting was a little fracture surface here where that was fixed. And then, you know, we had a fracture surface here where maybe we had some bending that came out of it. So can you kind of visualize that? It would like peel apart and just break more than likely if you had a big enough load on it.
Yeah.
And that's because what's going on right here is it's infinitely rigid, right? It's infinitely fixed. It cannot distort. We can't trust the stresses that's going on there. We don't know anything about that other than it's fixed. It's infinitely zero. We're setting it in mathematical terms, we're setting the traction equal to zero. Nothing is going on there. So what St. Venant's principle is basically going to show us is you can't trust anything at your boundary condition, but you can trust it a little bit away. And then there's a check that you can do if you go a little bit away and then you go really far away and you get some equilibrium. If you get force equilibrium, then your first point that you picked that was close to the boundary condition is good. You can trust the results. So if you wanted to, you could back up really, 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 really close to the boundary condition until you didn't get that equilibrium. And then you could say, nope, those are bogus. It's being affected because of my boundary condition. My elasticity professor would probably not like my oversimplification of St. Venant's principle, but that's my interpretation of it. So let's get into the details of it a little bit more, but that's essentially what we're saying. So I'm gonna do my hardest here to draw a cylindrical object. we're going to say that vertical is x2, horizontal out of plane into the screen is x2, or sorry, x1. And longitudinal x3. And we're going to say that this is a cut section. And our origin back here is O. And I'm going to pick another point on this surface here. And we're going to call this O prime or O1, if you will. And this distance here is going to be called L. And our bar is just going to call SL. So the body is S. This surface right here is our boundary condition, and we're going to call this S1. This surface on the end, we're going to call this S2. And we're going to create some random area in the middle. We're going to just call this S. And S is equal to any cross section between S1 and S2. What else do we have? O is at centroid. Of the cross section. Therefore, the integral of S1 x1 dA is equal to the integral of S2 x2 dA is equal to 0. What else do we have? L is typically much greater than in plane dimensions. So we can't use this St. Venant's principle on a thin plate, is what this is saying. Where let's say that our boundary condition is this bottom surface here, and then we're going to apply a load on it. I probably should have drawn this differently. This is a no-go for St. Venant's principle. It's too narrow. That if this is L, this is a for St. Venant's. Has to be long. Or a pretty far away. I'm going to use a notation 1 and 2 superscript on tractions. That does not mean squared. So let me write that. So traction, this, actually, yeah, I'll keep it this way. Does not mean and this is going to make some assumptions. So we're assuming linear elastic. So assuming linear elastic, nothing funky going on in our material curve. So we're going to apply a load that is below yield strength. So let me ask you, what I'm telling you right now is, so I'm telling you this is valid for linear elastic. I'm not saying it has to be linear elastic material. So let's say I'm dealing with the steel and, it has linear elastic material up to sigma y, right? Sigma y, and this is my sigma ultimate. What I'm saying is this is only valid for stresses and strains and displacements in the yield region right here. As soon as you load it to where you go plastic, St. Venan's is no longer valid for any of the plastic flow. So it's not a function of just material. It's also a function of your loading. If you take it into the plastic region, then you cannot apply the St. Venan's principle. So linear elastic, isotropic material, and it's homogeneous. Homogeneous body definitions. Meaning if you apply a body force to it, it reacts homogeneously with the material. There's not sections within the bulk of the body that would behave differently than something else. What this also implies is that our body force is equal to 0. We're saying that our traction is equal to 0 on SL. Where's SL? Yeah, on SL. I don't think I wrote the subscript. Yeah, I did. So the complete surface, the outer surface of the body is SL. So that means it's traction free around the cylinder. There's no tractive forces on SL. We're saying that the traction is equal to this traction superscript 1 on S1. So we're saying that on S1, we have a, we're basically we have a traction equal to 0, and we're calling that traction T subscript 1. And the traction is equal to traction subscript 2 on S2. So S2, the surface here, the traction is equal to 0. So no applied tractions on it. For existence of a solution, T1 and T2 must be such that the integral of S1 traction 1 dA plus the integral of S2 dA is equal to 0, which implies some forces equal to 0 and sum of the moments equals 0. So that is integral of S1 x dA plus and that's some of the moments. Equals 0. So now we're going to have a little bit of narrative, and I'll try to write nicer.
Yeah, what's the x vector there represent? That squiggly line?
That's the distance from the origin for a moment.
Oh, sorry, that was distance.
So Saint Venant's principle states the difference in static equilibrium, or sorry, static equivalent that states that the difference in static equivalent loads generate the same stress away from the boundary condition. There's more. We seek to solve this glass sorry, it's a class of problems in the sense of Saint Venant, i.e., we seek one solution that produces the same resultant force and moment on S1 and S2 as do tractions 1, tractions 2, but we still insist that our traction is equal to 0 on SL. And what this looks like is let our force vector equal the integral of S2 traction 2 dA, and our moment vector equal the integral of S2 x minus L E3, so that's stress, cross product, traction, second traction dA. So this is cross product. So this moment is due to the second traction about our origin prime, or our second origin. We're about done with this one. So there's four special cases, and I'm not going to go into the the theory or the proofs on these four cases, but the way this works is, if you have a real problem, you're supposed to try to simplify it or get it into a form where it represents one of these four special cases to see if St. Venant's principle is applicable or not. But they're pretty basic. So the first one is called extension. So F3 is equal to F, and F1 is equal to F2 is equal to 0, and moment is equal to 0. And that is simply a pure tensile extension load. The second one is bending. So our force vector is equal to our 0 vector, moment about 1. Our moment is equal, that should be vector, is equal to M1, and M2 is equal to M3 is equal to 0. This is moment. Torsion. F vector is equal to the 0 vector. And M1 is equal to M2 is equal to 0. And M3 is equal to M. And it's equal to the double 0. And then the fourth one is flexure. Moment vector is equal to our 0 vector. F1 is equal to F3 is equal to 0. And F2 is equal to F. So the idea is if you have a problem, you would try to break it up into a superposition of these different principles. So you would say it has extension and it has bending. Or maybe it has extension and torsion. So you'd kind of break it up that way. But essentially, well, we have a few minutes. So I'll go over the extension one and kind of show you that one. Yeah, that's one that we can get through, and it's probably the most useful. So for one, for case one, extension, it's simply, what we have drawn here is, we have a force, but that implies that we have a uniform distributed load, right? So force over area. So the way you approach this is you guess. You guess at the stress field. T33 is equal to F over A. And A is equal to the integral of S dA. All other Tij equals to 0. And our stress tensor is constant. That's just a fancy way of saying that this is not a dynamics problem. Our stress field is not changing. Okay. If our stress tensor equals a constant, then I'd like to point out the obvious. Our strain field is constant. Just by Hooke's law. Or constitutive equations, or however you want to call it. So E11 is equal to E22 is equal to minus Poisson's elastic modulus T33, and E33 is equal to T33 over the elastic modulus. Hopefully the E's don't bother you. It's faster for me to write than epsilon. I'm epsilon challenged. I can't write that for some reason. EIJ is equal to 0, and I is not equal to J. So the body is in equilibrium. We know this. Because our stress field is constant. If, try to visualize this. So you have this potato, and if the stress field was changing, that means your strain field would be changing and your displacement field would be changing, right? It would be actively moving. So you would have to have a load that is either is changing, which essentially makes it a time-based problem, and it's may or may not be in equilibrium because you're having rotation or massive displacement. Something is going on with it. So we can assume it's in equilibrium because T is constant. From our previous discussions of our equations, remember our columns 1, 2, and 3. You would need to verify that your stress field is compatible. So I'm gonna write this as a question. Is the stress field compatible? So remember our compatibility equation? What was it? Do you remember? Something like that. So this has to hold true to be able to claim St. Venan's. So you have to verify that. You also have to look for or enforce traction on boundary. Therefore, Tij Nj is equal to Ti is equal to 0 around the surface of the body. And then you find displacement. So displacement in the 3 direction is equal to our stress in our 3 divided by our elastic modulus times x3, so it depends on where we are in the length, plus rigid body terms. So if we have any body, any stress or any displacement that's coming from a body force, you would have to take that into account. Our displacement in our 1 direction is equal to minus Poisson's over elastic modulus x1 plus rigid body terms. And our displacement in our 2 direction, Poisson's E T33 x2 plus rigid body terms. Where T33 is still just equal to F over A. So that's what you would have to do to go through to see if you can claim St. Venant's, if it holds for an extension only case. Is you assume a stress field, it's just simply the integral over that area, and it's your force over that area. We assume all other stresses are 0, and then our stress field is constant. We can use Hooke's law because we have a stress in the 3 direction. Our stress is only acting in our 3 direction, so it's a pure tension. So we can get E11, E22, and that's due to Poisson's effects because it's a slender rod. So we're going to have a strain in our 1-1, in our 2-2 direction, in our 3-3 direction. All other strains are 0. So E12, E21, those are all 0. We're making an assumption, or it has to be true, that the body is in equilibrium. Stress field has to be compatible. So our partial derivative of our stresses plus our body force has to equal 0. We need to make sure that our tractions on our boundary are equal to 0. And if all of that comes into play, then you can calculate what your displacements are due to pure extension St. Venant's principle. So the same process can be done for case 2, 3, and 4. They're much more lengthy that you go through them. But essentially that's what you do is you break a problem down into these components. And you basically use superposition. So kind of a quick summary here. Well, let's see, then let's write this. For real problems, use superposition of St. Venant cases to find total displacement, strain, and stresses. So essentially you'll get axial plus bending plus torsion plus flexure. Equals total. If you can break it up. And if your problem doesn't use one of these, then it's 0. But you have to be able to break it up into those very, very purest type of loading situations. But in general, St. Venance is only valid for long slender prismatic members. Sure. So short, stocky plates and things like that, you wouldn't be able to claim St. Venant's principle. You have to move out away some distance from the boundary condition to claim it. But this is kind of the beginning to this complicated view of you can't trust the stresses that are at your boundary condition. You got to move a little ways away. So one of the things that you can do, you can look at the strain rate, you can look at how quickly or look at the displacement field, how quickly it's changing from your boundary condition. You really have, you'll have stresses and strains and displacements will be zero, but you'll end up with stresses that are going to like infinity, right at your boundary condition. They'll be really, really high. So you just back off until that it drops off to a more normal value. So, okay. So that's St. Venance. Not too exciting, huh? A long way of saying don't trust the stress at the boundary condition. Don't trust the strain at the boundary condition. So let's circle back to something. So let's say that you have this beam and you need to put a load on it. And let's say that you need to know what the stresses are going on here. How would you find out about that? What are things that you could do so you could evaluate the stress here? But let's assume this isn't a perfectly, something that you could do by hand. It's something very complicated. You're going to do by finite element method.
You could make it longer and then see what the stress is if you cut it at that length.
Yeah, and isn't that kind of the same thing that we showed with the St. Venance principle? Remember, we showed the cylinder with an origin. I mean, it was only a few minutes ago, right? And we basically said, yeah, we have this deal, and we have a cut in it, right? And we had some, some section here. What was this? S2. This was S1. What was this? I don't remember what we called this one. SL? No, that was the body. That was something else. Let's call this 3. So basically, that's what we're doing right here, right? So I want to know the stress here, and I'm saying I want to know the stress here. So yeah, it's exactly like that, right? So I can just make my beam longer. And if you wanted to get, real crazy with it, you maybe do something like this or, whatever. But essentially, you make it longer and you move your boundary condition away from it. Make your part longer, and then you can, trust the stresses that are going on right there. I mean, obviously, it's more complicated than this, but that's what you have to do. You have to move your boundary condition away from the part that you're trying to get the evaluation on.
Now, does this apply to FE code in any way besides just conceptually of how you would approach setting up your model? Does it actually apply to the FE code, this St. Venance, or just how you would think about setting up?
No, it does. It does. Because what St. Venance is really saying is you take a boundary condition, you're going to get infinite stresses there. You're going to get, crazy high. So you have to step away some amount in order to see if it's good or not. But you can't just look at it in one spot. You actually have to say, okay, I'm going to check it here and I'm going to check it here, and I'm going to compare those values. And that's how you can figure out how close you can get to the boundary condition. If you, let's say you didn't have the luxury of extending your part and you really needed to find out how close can I trust the data coming out of that bound, close to that boundary condition, that's what you would do. You check it, maybe you do your verification, your maybe, because we're comparing T1 and T2, right? Maybe you compare, maybe this is T1 and this is your T2. You're comparing those two results within the body of the material. And if you don't get the validation or the equilibrium and stuff that we were looking for, the force balance that we were looking for, well, then you would have to come out here and say, okay, I need to move my T1 out further to try to trust the results.
This is something that like a code built into the actual code and not just what the user is doing?
Not that I'm aware of, no. It's just
Okay,
something the user's doing, yeah.
It's just something you want to know as a user as opposed to FE code.
Yeah, and I think what most people do is you would just look at your, essentially you're looking at the partial derivatives, right? You're looking at the rate of change of the stresses and display and strains in your results. So, if you go from, stress values here or something that are around 1,000 megapascals, and then all of a sudden you're at 100, there was a very, steep change there, a big rapid change there. So it tells you that that stress field is not something that you can count on. It's not realistic. There's still boundary condition effects going on in that area until you get away a little bit further. So, and that goes for wherever you have applied a boundary condition. So if you have, for instance, you have a plate, maybe you've done something in finite element world where you have like top view plate or something, you have a plate and you're applying a distributed load to this. And let's say for whatever reason, you created a boundary condition in a hole here. Actually, those aren't arrows. I meant to show these as a fixed boundary condition. You're essentially, based on St. Venan's, you probably can't trust anything in here and anything around here, and you get this elliptical shape out of it too that you can't trust because of boundary condition effects. So you really have to be careful with how you do your boundaries and things like that. And in fact, with this problem right here that I'm showing, if you were to talk to like a super theoretical person, they would say that you should do this this part in, you would section it in a quarter to avoid that. You wouldn't analyze the whole plate, and then it would simplify boundary conditions, because then you would be looking at and you would have a fixed boundary condition here and a fixed boundary condition here. And here would be an equilibrium based on there. So anyway, we're over. I apologize for that. I hope you have a good night. So Thursday, we'll do plane stress, plane strain. So thin plates, thick plates. One of them, you assume stress is constant through the plate, and the other one assume strain is constant through the plate. So out of plane strain versus out of plane stress. So it's just some rules of thumb depending on if it's really thick material or really thin material that you can make. and then we'll be ready for break. Okay. Have a good night.